Uh, Sorry for it. Yeah, it took time arranging the Zoom setting. The computer is actually the computer status was not good. So I think we can start now. So in the previous class, we learned about the reliability and instruction set architecture of computer systems. Actually, I mentioned that the reliability is getting more critical in the modern computer systems. So it is because of the semiconductor technology now. So it means that the size of transistor is getting reduced. So actually, which means that the amount of charge stored in this small size transistor is also being decreased. So that's why the reliability issue is getting more critical. And then, for example, so recently we are we can use the DDR5. So actually DDR5 supports the higher clock frequency. Also DDR5 supports the high bandwidth, but in order to support this fast DDR, so fast DRAM. So the size of the capacitor and also the size of the MOS transistor in DRAM cell is also shrinked. So which means that the reliability issue is getting critical in DDR5. So DDR5 is using ECC logic actually. So it's called the in-DRAM ECC. So it's ridiculous because ECC module is the ASIC module, so it's different from the DRAM manufacturing process. So it means that the cost of the manufacturing increases for DDR5. So also in the previous class we talked about the instruction set architecture, and then actually I briefly introduced the basic instruction sets which will be used for this course. So these instructions are similar to the MIPS style. So which means it's a RISC type. And then, but usually most of modern processor now using RISC type instructions. So you may think that the most popular processors in the real world is x86 processors. And then, the x86 ISA is the RISC type ISA with a complex instruction set architecture. But inside of this modern Intel or AMD processors is very similar to the RISC type processors. So which means that the complex instructions are decoded into the very simple instructions, simple RISC type instructions. So actually in the processor, the multiple instructions, so these multiple simple instructions are executed instead of there is complex instructions. So in the so we may think that the RISC type is a very complex instruction set. So which means that the RISC type instructions also make the hardware structure very complex. But nowadays it's not true. So actually we thought that the characteristics of ISA also influences the performance of the processor, also the manufacturing cost. But it's not true now because the most of the processor is employs the RISC type processors. So, and then in this time we will discuss about the static pipeline architecture. So actually, this static pipeline architecture is very similar to the 5-stage pipeline architecture we learned in the undergraduate course. And then actually, so in this course, we will learn about the the process architecture. But first, we need to know the basic structure of the the static pipeline architecture, and then also the out-of-order processor is what was developed from this static process architecture. So we need to know the issues and then some properties of the pipeline architecture actually. So actually, so we call the 5-stage pipeline processor is the pipeline processor, and then also we call the bottom process architecture is the out-of-order process architecture. But actually, the out-of-order process architecture also employs the pipeline, and it's true actually. Most of the system employ a pipeline architecture. So actually, the out-of-order processor is called dynamically controlled pipeline architecture. And then, as you can see in this title of today's class, so the 5-stage pipeline processor is a simple pipeline processor. It's called the statically scheduled pipeline processor. Okay? So, and then I call it as the static pipeline processor. Okay, so let's start from the 5-stage pipeline processor. It's very popular, and then I believe most of you are familiar with this 5-stage pipeline because it's very, very popular. And then, so there are 5 stages in this 5-stage pipeline architecture. These stages are instruction fetch, instruction decoding, execution, and memory stage. Actually, the memory should be accessed by data transfer instructions, so it requires memory stage also, and then write back stages. So actually, these stages are required for executing every instruction. So actually, every instruction has these stages. Okay. This figure shows the architecture of the 5-stage pipeline processor. But I believe you are very familiar with this figure actually. And then also you need to remember that this is the pipeline architecture. So which means that instructions pass through every stage, from instruction fetch to the write back. And then with these instructions, control signals are also delivered to the every stage along with the instruction. Okay, so actually this is the basic scheme of the pipeline. So pipeline structure in the digital system. So which means that instructions and the operands are propagated through every stage, the stages to stages, and the control signals, required control signals are also passed through the every stage along with these operands and the instructions. So you may design some other digital systems, not the processors, but it's also this can be also applied to the other digital system design, which means that so actually the purpose of the digital system design is to process some data, so digital data. So which means that we also propagate some data, which means the operands along with some functions or processing, and then these systems also require control signals. So for every stage, control signals and operands are propagated along in a set. Okay, so you can, of course, instruction carries its baggage. So which means that the instruction also propagate to the next stage with the control signals. And then in the pipeline process architecture, let's focus on the data dependencies. So Data dependencies means that formal instructions may generate some data, or the formal instructions may require some operands. And then the following instructions may require the result from the formal instructions, or the following instructions try to write the data to the same place with the formal instruction. So we need to focus on the three types of the data headers actually, because if we consider some instruction type, so for example, the very simple instruction like add R1, R2, R3. So if we just see that this instruction, so this instruction equals to two operands from the register file, and then this is the destination register. Okay. The result of this add operation is stored to the destination register. So and then we also know that a program is a group of many instructions. And then when you write a program, actually every statement in our high-level language code has dependencies. It actually it's obvious. So like A equal 1, and then B equal 2, and then C equal A plus B. So we can easily find the dependencies between every line of our code, also every statement in our program. Then actually the computer processor executes the instructions compiled from the high-level language code. Because the high-level language code also includes the data dependencies, our instructions, compiled instructions also have dependencies. And then these data dependencies should be maintained. It's very important. Is it because what is the definition of the processor? So actually the definition of the processor is that the processor receives the instruction, and then when the instruction is executed inside of this processor, then state of this processor or state of this computer system is changed. And then which state? So I mentioned that only the register file data, and then the data in the main memory are changed by instructions. So actually, when the instructions are executed in the processor, serially, then we need to maintain the order of changes in this state in the processor. So it means that we need to maintain the dependencies in the data, and then we need to focus on the three types of data actually: the read after write, sorry, write after write, and then write after read. So actually, sorry. In a static pipeline processor, we just focus on the read after write header for the register file. This is because if we just focus on the static pipeline processor, so 5-stage pipeline processor, the register is read in the ID stage, and then register is written back in the write back stage. So there are time gaps between instruction decoding and then write back stages. So we need to focus on the data dependencies in the register file. Then how about the memory? So when I explain about the definition of the processor, so I mentioned that only two data in two memory storage components, such as the register file and the memories, are changing. So it means that we need to also focus on the data dependencies in memory, the main memory. But in the five-stage pipeline processor, we did not learn about the data dependencies in main memory. Why? Right. It is because when I explain about the hazard, hazard in the register 5, so I I mentioned the time gap between the register read and then register write. So register read occurred in the ID stage, and then register write back is performed in the write back stage. And then there is a time gap between the instruction decoding and then write back stage. How about the memory? Actually, the five-stage pipeline processor, the memory stage, we can only find only one memory stage. So this means that the memory is handled only in the memory stage. So actually, in the memory stage, the instructions that handles this memory, the main memory, is the in order. So it's so the extra instructions access the memory sequentially. The order is maintained. So which means that also we assume that every accesses to this main memory is atomic. So which means that when an instruction is executed, the result of the instruction is reflected immediately. So that is the definition of the atomic. So the memory is accessed in order, and that means the sequentially, and then this order is maintained. And then memory has only one stage, so we don't need to consider the data dependencies in the main memory. Okay, so which means that the process architecture is very simple. So we don't need to consider the data dependencies in the memory components. Now, in the five-stage pipeline, we just consider the low hazard, the read after write hazard. So why that data dependency is so important? The computer processor needs to generate the correct answers, the correct result. But data dependency is not maintained, then our processors may generate the wrong result. This is very critical. So that's why this order, the order of the data access and the order of the data updates are very critical for this process architecture. Also, there are two other types of hazard, so like structure hazard and then control hazard. And then also in the five-stage pipeline processor, we cannot find any structural hazard because the structural hazards are caused by lack of hardware resources. So which means that this is some hardware. The hardware has the limited resources. And then some instructions try to use these hardware resources. And then the other instructions try to use these hardware resources at the same time. This is the structure hazard. So which means that we need make these some instructions delayed due to the lack of hardware resources. But in the five-stage pipeline architecture, every hardware components are used every stage sequentially. So we don't need to consider about the structure hazard. But in a real hardware, so that's actually we learn about the out of the process architecture, then we need to consider also structure hazard. And then control hazard. Control hazards are very critical. So because when the branch is performed, also the branch instruction is taken. So it means that the condition of the branch is true. Then clock cycles are also wasted. This is because we need to cancel the instructions after the branch instruction. So control hazard because of the branch instruction, the clock cycles are wasted, and this is also very critical for the performance of the processor. So, why did I mention is pipeline hazard? Actually, our research, process architecture research, focus on some solving the performance avoided by this hazard. Actually, the most of the process architecture research focus on reducing hazard in the pipeline, the architecture. Data hazard, structure hazard, and the control hazard. So those hazards are very critical for the performance. So actually, the pipeline stage is very simple, and then I believe everyone can understand how pipeline works. But because of the hazard, and then we we apply many architectural techniques to reduce hazard. And then actually these ideas are very complex, and so it means that the structure architecture of the modern processor is getting more complex. So actually, but the research is hard. Actually, fundamentally hard because we need to solve some problems in our real world, and then no one knows answer for this problem. Okay, so that's why research is hard. So let's briefly review some data hazard in the static pipeline processor architecture, the 5-stage pipeline architecture. So I mentioned that in the 5-stage pipeline architecture, we can only find low hazard. So low hazard means that read after write hazard. So which means that the following instruction requires some operand from the former instruction. So which means that the destination of the former instruction is identical to the source, one of the sources of the following instruction. So that's the low hazard, the read at the right hazard. And then, so we already know the solutions for this low hazard. So we can implement some data forwarding logic. So which means that when the data is ready, and then before this data is written back to the register file, this ready data can be used for the operand of the following instructions. So this is the definition of the data forwarding. And then this data forwarding is also very important. So that the fundamental base of the data forwarding is that if a processor already have result or some required data for the following instruction, and then this data can be used by following instruction, so the future instructions. So this is some fundamental base of the data forwarding. So why is this important? So actually, in the pipeline process of data forwarding is very simple. Okay, so we can make the data forwarding path from execution stage to the another execution stage, so like this execution and memory pipeline to the input of the ALU. Also, we can make another data forwarding path from the memory pipeline register to the input of the ALU. Also, we can also implement the internal forwarding in the register file. Okay, here. But actually, the data forwarding is very simple. The 5-stage pipeline processor. But in the out of the processor, data forwarding is critical. So I said, so the fundamental basis of the data forwarding is that if the data is ready, if a processor already knows the result of the previous instruction, and then before this instruction is updated to the register file, so that is the architectural state or even memory, then we can use this data. But the future instructions can use this data. So in the statically scheduled pipeline architecture, we can make the static, so that means the fixed data forwarding part. But in the out-of-order processor, so this fundamental base can be also applied to the out-of-order processor architecture. So which means that if the data is ready, and then if this data, even though this data is not updated to the architectural state, but the processor can utilize this data. So that's it. So in the out-of-order processor, there are we can also implement the data forwarding, and then actually this data forwarding is frequently used in the processor. Okay, so data forwarding is very simple in the 5-stage pipeline architecture, but in the out of the processor, it's a little bit complex. But I believe the fundamental base is very simple. Okay, data is ready, and we can use this data, even though the architectural state is not updated. So we can also have a row hazard. Row hazard is very simple, and then also in the 5-stage pipeline architecture, we cannot solve the load hazards between load and following instructions, because the load is performed in the memory stage. So in this case, we need to store pipelines. Okay? Very simple. So this is the structure of the pipeline processor, 5-stage pipeline processor. And then so now to handle this load hazard for data forwarding, the pipeline processor has the forwarding unit here, and then the hazard detection. Okay, the hazard is detected, and then if this hazard cannot be handled by data forwarding, the pipeline stages are stored. Yeah. So control hazards. So control hazard is caused. Control hazards are caused by branch instruction. So the result of the branch instruction is changing the program counter. So which means that the instruction streams executed by processors are changed by branch instruction. So if the wrong instructions are fetched and decoded in the pipeline stages, then these pipeline stages are flushed if the branch instruction is taken. So if some instructions are flushed from the pipeline stages, then the cycles for the corresponding instructions are wasted. So it works as the performance bottleneck in the processor. Okay, and then actually in the real process architecture, exceptions are sometimes exceptions is critical. It's not critical because a processor may need to support precise exceptions. So precise exception means that, so actually the every instructions like add, sub, load, merge, store. So this is some instruction streams. Like add, sub, load, move, and store. So I cannot write. Why? Actually, every instructions can generate exceptions, and then actually the exceptions should be handled in order. sequence, that means that sequentially. So, which means even though the exception can happen in row instruction, also in the add instruction concurrently, then we first handle the exception by this add instruction, the formal instruction first, and then we need to handle the exception by load instruction. So that means that the order of exceptions also should be maintained. So it's important in the process of design. Many exceptions must be precise. So this means that the order of exceptions. So exception handling should be in order. So it's a synchronized and then resumable. So which means that if the exception is effective, and then the exception is effective exception is handled by exception handler, then processor need to go back to the original program, original thread, and then also the processor need to record the states of the original state, and then processor resume the execution of the following instruction. So that is, which means the synchronized and then resumable. Also, so this is very important. So most of the processors need to support precise exception. And then in order to support this precise exception, the state changed by instruction should be in order. So the order should be maintained. So 출판에 안 쓰는데요? 줌에만 쓰고 있습니다. 네? 아, 여기 나를 덕분에 바로 보네. Okay, so actually the out-of-board processor and the modern processor need to support the precise exception, but actually when the processor is executed out of order, then it's not easy to support the precise exception. Actually, it's very critical also for the out-of-order processor architecture. So supporting the precise exception is somewhat challenging. Okay? But it's a critical issue, okay, for the processor design. So, and also, as I explained, the control bits, control signals are also proceed to the stages of the pipeline processor with the instructions. Okay. Then also, actually I already explained about these mechanisms. Okay, so like data, so we can solve the data hazard issues with the data forwarding, and then the data hazard cannot be solved by data forwarding. Can we need to make pipeline stages stored, and so the stage processing is required when the branch instruction is taken. Okay, this is the main concept of the simple pipeline, 5-stage pipeline architecture we run in the undergraduate course. And then let's see some more complex and more advanced some architecture. So this architecture is also a statically scheduled pipeline architecture, but this architecture is a little bit different from the 5-stage pipeline architecture. So let's consider about the floating point unit. So actually the data type of the floating point unit, floating point is different from the integer type data. So actually, so integer type means that, so this is the 정수. So you know, the integer type data is very simple, and then we can implement also very simple hardware, the arithmetic unit for integer data very simply. So which means that if the hardware is simple, so which means that this hardware consumes small number of cycles. So actually we assume that the arithmetics in the integer type data is handled by ALU, the arithmetic and the logic unit, and then the ALU is in the EX stage, execution stage, and then we assume that EX stage only consumes one cycle. So it is because the hardware structure. The hardware structure of this integer arithmetic unit is very simple. But how about the floating point? The floating point type data is more complex than the integer type data. So which means that the floating point unit is more complex than floating point, which means the floating point unit consumes more cycles. So actually, because the data type is totally different between the instruction type data and then floating point type data, actually processors have the separated register file, such as the integer type register file, and then put register file for the floating point data. So there are two separated register files in the ID stage, and then if the instruction is the floating point type instructions, then it goes to the pipeline stage for the floating point unit. And then, as you can see, you can find that the floating point unit consumes more cycles. Like in this example, the FPU consumes five cycles. So which means that the number of stages for this floating point unit is larger than the number of stages for the integer type instruction. So what does that mean? So here, actually, in the ID stage, there are two separated register file and I then RFF here. So problem is that the process architecture get more complex. It's more complex. Also, we serve the data header to the data forwarding. But actually, the data forwarding was very simple for the 5-stage pipeline architecture. Like we can implement the data forwarding from this pipeline register to the actually this is the before the execution stage, the ALU. Then also we can implement the data forwarding here. This is the forwarding modes. Also we can actually we can implement the data forwarding path from here, 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 here. And how about the floating point instruction? We need to implement the data forwarding from here and then here. And then, but even though the floating point arithmetic units are pipeline, we cannot implement the data forwarding path inside of the floating point pipeline stages. Okay, so which means that the data forwarding path gets more complex, and then we need to also detect that is some complex data forwarding relations, and then support the data forwarding. And then another issue of this different pipeline architecture is that it's actually out of order completion. What does that mean? So this is the integer type instruction pass, and then it will take 5 cycles from instruction fetch to the write back. But how about the floating point instructions? The floating point instructions will take this path, and then it will take more than 5 cycles. It will take 9 cycles. So based on the instruction type, the instruction completion is the out of order. So that means that the completion, the instructions are fetched in order. So fetched in order, and then decoded in order, and then even the instructions are executed in order. But the completion of the instruction is out of order. Okay. And then actually this out of order completion cause many issues. So that's the, and then not to solve this issue, we need to apply the more complex architecture. Okay. So actually, we can. I already explained that we can solve the some data hazard with the data coding. So we need to understand some required time gaps for the former and following instructions. So we need to, which means that we need to understand the latency and then interval of the instructions. So the latency means, so actually you can, I believe everyone can understand the meaning of the latency. So latency is the time gap between time difference between the start and then end of the execution. So and then the interval means that it's when the instruction is given to the arithmetic unit is the execution engine, then interval means that the time gap between the former instruction and the very next instruction. So this is called the interval. And then the latency and the interval can be different. And also it's true for the pipeline architecture. So in the pipeline architecture for the normal instructions, like the integer instructions, the latency of this instruction is actually 5 from instruction fetch to the write back. But interval, so interval is just 1. Okay. So that means that in every cycle, every instruction can be fetched and issued. So this is the interval. So actually, based on this latency and then interval of the operation, we can make we can design the data coding unit, or so we can design some hazard detection unit. Okay. So actually, in this slide shows some examples of the latency and then interval. So if the instruction uses the integer ALU, the latency is 0. So actually, so we think that the latency is only 1 cycle, and then this latency is that when the result is ready. Okay, so which means so think like this: if the add instruction, sorry. So The formal instruction is the add instruction like R1, R2, R3, and then the following instruction is also add instructions on R4, R1, R5, like this. So we can find, oh, there is the data dependencies, the data dependency between these two add instructions. But we know the following instruction, the following add can be executed just after this add instruction. So actually the latency, which means that when the two add instruction is executed, we don't need to consider about the data dependence. So because there is data boarding path in the this pipeline processor, and then is using this data boarding path, the data dependence, the low hazard can be solved. So you don't need to consider the latency of this integer and AAA. So it means that this latency means that it's the required cycles between two dependent instructions. Okay, so it means when the two add instructions are repeated, two different integer type arithmetic instructions are used, then we don't need to consider about the low hazard. Okay, so cycles will not be wasted. But and then interval. So interval is just one. So which means that when this add instruction is issued, and then the following add instruction can be issued just after one cycle. So that means the very next cycle. So how about the load instruction? If the formal instruction is a load instruction, and then the following instruction requires data from this load instruction, then we need to store one cycle. So this is the required latency. It's the one. And then what interval is just one. So which means that the next instruction can be issued right in the very next cycle. How about the floating point instruction? The latency is 4. So these and then interval is the 1. So which means that if the floating point unit is the pipeline, then instruction can be issued every cycle. So we can think about the latency, the required latency, and then interval of the two different instructions. And then, so actually, when the compile optimization is applied to the statically controlled pipeline architecture, then compiler needs to consider this information, like latency and then interval of the instruction. Why? The statically scheduled pipeline architecture. So if you think about the name of this processor architecture, statically scheduled, which means that the hardware does not schedule any instruction. So which means that the hardware issues the instructions in order, and the hardware does not know about the completion time actually. So in this example, the floating point unit requires more cycles. So actually the completion is out of order, but hardware does not consider about the scheduling of issue of instruction. So which means that the hardware just receive the instruction and execute the instructions in order. And then in order to increase the performance for this hardware, this processor type, then compiler needs to apply some optimization techniques. And then not to apply the optimization technique like the instruction reordering or some other techniques, such as the loop unrolling, then compiler needs to know the information like this. So which means that If the former instruction use the integer ALU, and if the data dependencies, then the required latency is 0. Which means that compiler can add any dependent instruction after this integer type A instruction that use the integer ALU. And then also, if the instruction use the memory, then it's a load instruction, the latency is 1. So which means that compiler can insert any independent instruction between these two dependent instructions because the latency is required latency is 1. But the floating point is a 4. So in order to optimize this code, the compiler needs to reorder the instruction orders. So then compiler need in order to apply the optimization technique, and compiler need to find 4 independent instructions to improve the performance. Okay, so in the statically pipeline processor, the hardware does not consider about the scheduling of the instruction, but compiler needs to consider the order of instructions. Okay, and then which means that compiler needs some information from the hardware, like this. And then, actually, I mentioned that we don't need to consider about the structural hazard in the simple pipeline, 5-stage pipeline architecture. But the problem of this out-of-order execution compilation is, so which means the floating point requires the more cycles, then we need to consider about the structure hazard, which means, the process architecture is getting more complex. So what kind of structure hazard? Like the white bag. So actually we can find the structure hazard for the register file. So actually the problem is that even though the floating point register file is accessed, it's updated, load instructions, load single precision, like LS. So the floating point type load instruction has through this path. So which means that this load instruction go through this path, the upper path. So actually the load instruction requires only five cycles. Okay, if the data is found in the error cache. But how about the floating point type arithmetic instructions? Like here, the add single precision. So it requires the floating point units, and then it will take 5 cycles of the execution stage here. The problem is that for this add instruction, and then for this add instruction, so the adding instruction is here, and then for this write back stage, the I1, the former add instruction, try to write data to the floating point register 5 in the cycle number 9, and then this load single precision. Load single precision also try to write the data to the floating point register 5 at clock cycle number 9. And then if there is only one port for the write operation in the floating point register file, and this is the structure hazard. So we need to avoid this situation. So which means that the load instruction, the completion of the load is actually write back of the load instruction to the bit delayed, because actually in this example the add instruction is the former instruction. So actually the add instruction has a higher priority than the following load instruction. So since that the load instruction should be delayed, okay, here. And then how many cycles? Actually, if one cycle is delayed, and then it conflicts with also another add instruction here. So problem is that it's very complex. So in the out of order completion, then we need to also consider the additional hazards. So you make some. So actually, the 5-stage pipeline is very simple. So we don't need to consider many aspects of the pipeline processors. Actually, it's a 5-stage pipeline processor. But in this, even though the out of order completion is applied, like so, in order to support the floating point type instructions, then we need to also consider many many different hazards in our processor architecture. So this type of hazard should be also considered. Same actually. Also, we need to also find the new data hazard. So another hazard is the wow hazard. So this is the right after right hazard. So why? The completion is also out of order. So which means that during two instructions that have the different latencies, like also the load instruction, which is the load double word, and then add instruction, floating point add instruction has the different latencies. Like so, it is 9 cycles, and then it requires the 5 cycles. So what's the problem? We need to consider also wow hazard, right after right hazard. So what does that mean? So in this example, this add instruction tries to update the data in F2. Also load instruction tries to update data in F2. But the load instruction will take 5 cycles, then add instruction will take 9 cycles. So which means that the instruction is complete. No, the load instruction complete here in this cycle, and then add instruction will complete after load instruction. So what's the problem? We try to update the same register file F2, but if the this update is complete just after the completion of the instruction, then so F2 you have incorrect data, so wrong data. So this case also should be considered in the out of order completion. So what does that mean? It's a statically scheduled pipeline architecture. So only the different thing from the 5-stage pipeline architecture is that we have a floating point unit which require longer cycles. So which cause out of order completion, and then when the out of order completion is included in the pipeline architecture, then we need to consider the structure hazard. Also, we need to consider the wow hazard, new type of data hazard. So how can you solve this wow hazard, right? About right hazard. Okay, so I made it. So actually, we need to maintain the order of register updates. So actually, the possible solution is to delay. So actually, it's a pipeline store. So and which means that this load instruction should be stopped not by the stage until this wow hazard is resolved. So which means that in this case, actually, so in the initial baseline, it's a very simple 5-stage pipeline architecture. It just considers the low hazard and then also control hazard by the branch instructions. But this out of order completion is applied, then we need to also consider some different data dependence, different type of low hazard. Like which means that the low hazard have the different latency between the former and following instructions. Also, we need to consider this wow hazard. So if this case is detected in the ID stage, that's because the hazard detection unit exists in the ID stage, and so we need to also detect the wow hazard cases, and then if the wow hazard is detected, then the following instruction to be stored in the ID stage. Okay. But we don't need to consider about the war hazard double right at the read hazard, because the register read, even because the register read is the in order. Okay. So actually in this case, we don't need to consider about the war hazard. And then also we can consider some more different type of low hazard as I explained. So in this case, the store instruction receives the data from the floating point arithmetic instruction. So actually the result, the data, the apparent for this store instruction is ready after the clock cycle number 9. So in those consider this data coding. So which means not data coding, which means if the store instruction is just after this multiply instruction, then store instruction need to be stored in the ID stage, considering the data hazard. So low hazard between the multiply and store instruction. Okay. So, and how about the memory? So I already explained that we don't need to consider about the data hazard inside of the main memory, because the memory stage has only one cycle, and then every memory data transfer instructions access this memory stage. So you don't need to consider what the data hazard in this case, because accessing the main memory is in order. Then you don't need to consider what the data dependencies in the main memory. Okay. So this is very important. So actually, when you consider about the data dependencies, we need to consider about the data dependencies in the register file, and then data dependencies in the main memory. This is very critical, because if the data dependencies cannot be maintained, and then computers will generate the incorrect results. So actually, when the processor is designed, then we need to consider to maintain the data dependencies in register file first, and then also memory stage. But this is the statically scheduled pipeline architecture, and as you can see, the memory stage is here, and then the memory instructions access this memory stage in order, which means we don't need to consider about the data dependencies in this case. It's very important. Actually, in the outer world process architecture, like the Thomas algorithm or some speculative execution is considered, then actually the accesses to the main memory, actually it's a data cache, can be also out of order. Then we and we need to check the dependencies between load and store instructions in this case. So it's actually very complex, okay? Because memory is very large compared to the register file. So that's why the data dependencies in the main memory is more complex. Okay? Actually, for the architectural register file, we just consider the register numbers in of the architectural registers from 0 to 31 for the RISC file. But the main memory, space is very large. So for example, if we just consider the virtual memory, so actually Intel, not the current generation. So actually the 64-bit computers processors support usually 48-bit addresses for the virtual memory space. Essentially, instead, we need to check the addresses of this memory space. So actually, it's not easy. Also, you don't need to consider the every case for the data dependency in the memory space. Okay. So actually, in the out-of-board processor, this is the critical issue. So then, how about the control hazard? The branch instruction pass through this path, so we don't need to consider about the control hazard in this case, because branch instruction goes through this upper path. Okay. So let's take a break for 10 minutes, and then I will resume the class. What time is it now? At 52. Let's take a break for 10 minutes.
티저 같은 경우는 레이턴시가 없다고 보는데 무슨일로 레이턴시에 required between dependent instructions. 이게 두 개의 차이가 잘 이해가 안 돼요. 이 메모리 스테이지, 그러니까 로드가 아니 메모리 스테이지, 라이트백 스테이지를 두 개 묶은 건 아니에요.
여기서 보완해 줘. 그러니까 한 사이클만 기다렸다가 하는 거죠. 어차피 데이터는 여기서 나오잖아요. 그러니까
근데 이제
로드가 있으면 이 로드를 받는 인스트럭션 여기 있으면 못 받잖아요. 그러니까 얘는 한 사이클 늦게 들어가야지 여기서 나오는 걸 받을 수 있는 거죠.
이 디펜던트 인스트럭션이란 말이 이게 서로 이어져 있는 따라오는 인스트럭션 바로 오퍼랜드로 받아야 되는
디펜던트 인스트럭션 때만 고려를 해야죠. 아무런 디펜던시가 없어 그냥 바로 시켜낼 수 있죠. 디펜던시가 있을 때만.
디펜던시를 고려를 했을 때 이제 사이클 이 시스템에서 결정되는 레이턴시를
그만큼의 이제 레이턴시를 고려해줘야 된다. required additional latency.
레이턴시 정의가 이제 디펜던트 인스트럭션을 이용해서 구하는 거죠.
네, 그렇죠. Can you see my screen? Okay. Let's resume the class. Okay, so now we are learning about the statically scheduled pipeline architecture. It's so long. The name is so long, so we call it as the static pipeline architecture. just use the 3 words instead of 4 words. So, actually this actually we learned from the 5-stage pipeline architecture. So this is very simple, and then so actually we used this type of the process architecture for the very first processors. Actually, very simple processors, and then the modern processors like actually it's very old also, like Intel 8286 or 8386 used so I believe actually this is the real processor, which means that this statically pipeline architecture is also employed in some very old commodity processors. Okay, so and then actually in the next class we learn about the Thomas algorithm and then the out of the processor architecture. It's very dangerous. So actually it starts from this statically pipeline architecture. So the main challenging is the data dependencies, like data dependencies in the register file, and then data dependencies in the main memory. Also, another challenge is some hazards such as the control hazard and the data hazard. So those are very critical issues. And then outside of this type of issues, many researchers applied some new architectural techniques or some new compiler optimization techniques. Okay, but it's important to understand some advantage or disadvantage of this type of processor architecture, like a statically scheduled architecture. Also, you will learn about the out of the process architecture. So you need to understand the pros and cons of this type of process architecture. So, and then in the out of the compilation, so it's also a static pipeline architecture, but as the floating point units are included in this instruction path, then we need to also consider the issues by out of order compilation. So as I explained, we need to also handle the additional hazard like a structure hazard and then wow hazard. So actually, we can detect the structure hazard because in the statically scheduled architecture, then every instruction. So as I mentioned in the previous slide, every instruction have some latencies and also intervals. We can find some information here, like latency and intervals. And then based on this information, we can check the structure hazard. Actually, as I mentioned in some example, like between the load instruction and add instruction, the floating point add, then we can easily detect the structure hazard case actually in the right back. Because think about this out of the compilation issue. Actually, every instruction is fetched in order, then decoded in order, which means that every instruction is issued in order. So issue means that instructions are given to the processing engines like ALU or FPU, so it's called issuance. Issue actually, it's verb, and then the noun form is the issuance. So issue means that the instruction is given to the processing engine and the processing unit. So, statically scheduled pipeline architecture, every instruction is issued in order. So we don't need to another issue. So we don't need to consider about the structure hazard and the processing units such as the AAU and the memory and floating point units in this case. So actually we need to consider the structure hazard in write, register write. So it's the write back. Then we can easily check this structure hazard using some latency, which means that the required clock cycle for completion. Okay, so we can detect the structure hazard simply, and then low hazard. So we can solve the low hazard with the data forwarding, and then if the low hazard cannot be solved by the data forwarding, then we need to detect the low hazard. So low hazard actually it's relatively simple because we can just check the latencies. Also here, this information, so it's a latency information, and then also we can check the data dependencies between two instructions, like destination register or the former instruction, and then the source registers of following instructions. Okay, and we need to check the wow hazard, the right hazard. And then we can also simply check the wow hazard like the low hazard. Okay. Okay, we can just check the destination registers of two instructions. Okay. So if the wow hazard is detected, then it is also stored in the ID stage, which actually we can handle wow hazard like the low hazard, like W hazard. But actually, the wow hazards are very rare. So actually, this type of instruction, so think like this type of instructions. So this is example. So it's very ridiculous. So add stores some data to the F2, and then just after that, the load instruction, the floating point load stores the new data to the F2. Actually, this is the ridiculous case because actually the wow hazards are very rare because we don't write the code like this. Okay, but wow hazard need to be detected. So actually the computer processor need to generate the correct result. And then if this is not made, if this line is broken, then we cannot use this type of processor. So think like this. So actually the Intel has the division bug in the very old processor. It's a very old processor. I believe it's about, so I think it's a bug in the Pentium processor. And then actually the Intel just, and when this bug, the division bug is firstly found, Intel thought that, oh, this case is very rare, so it will happen frequently. So Intel thought this is very rare, so they did not handle this case. But the problem is that some mathematicians find that, oh, this type of bug can happen more frequently. It's not rare, so this means that it's rare. So it's true. So that means that this bug happens very rarely, but it can also happen. So actually, the Intel fixed this bug, and the problem is that this is the hardware bug, so we cannot fix this type of bug. But actually, Intel was not able to fix this bug in the software, so Intel actually returned or changed the processor, which have the this type of bug is a division bug. It's very famous. So in that year, Intel's revenue was actually minus. So it's a very famous bug in the process of design. So the lesson is that, oh, this bug is it's not frequently happen. So it will not happen frequently. So it's very rare. But processor needs to also support these corner cases. Okay. Even though this is rare, then the processor needs to generate the correct answers. So this means that we also need to consider wow hazard, even though this event is very rare in the processors. Another critical problem is precise exceptions. So I mentioned that the processor needs to support precise exceptions, but in the out-of-order completion, the precise exception, supporting precise exception is very difficult. So let's see this example. So, this is the floating point add, and then this is the integer add. So this is the floating point add. So this add need to use the floating point union, and then this add is the integer. What is the problem? Actually, it will take 5 cycles. The floating point add will take 9 cycles, and then integer type add will take 5 cycles. So which means that from instruction fetch to the byte back, it will take 9 cycles. And this integer will take only 5 cycles. So what's the problem? We consider the precise exception. So how can you handle exceptions? So we need to think like this. So actually exception is the way. So first, the exceptions are very rare cases. And then, but we need to support the exceptions. And then, how can we handle the exceptions in the 5-stage pipeline process? So, when exceptions are detected in the formal instructions, then we need to call exception handler. Okay? And then, how about the following instructions after the exceptions? The result by following instruction should be cancelled. So which means what are the results by following instructions? So which means that it's the changes in register file or main memory. So actually, we need to cancel every result by following instruction when the exception happens for this instruction or certain instruction. It's very critical. Why? If the exception is handled by for this instruction, then we need to resume the execution of the following instruction. What's the problem? If the architectural states are changed by following instructions before exception is detected, then after the exception handling is completed, following instructions will generate incorrect results because the architectural states are already updated by these instructions. That's a very critical problem. So then what's the problem? This add instruction complete each operation in 5 cycles. That means that this add instruction. Let's see this table. And this add instruction is executed at just at the floating point add instruction. Add instruction write its result at clock cycle number 6. But that also assumes that exception happens at this cycle, clock cycle 7. So what will happen? So we need to handle the exceptions on exception by this add instruction, but the exception is detected at clock cycle 7, like in this stage. So in order to handle this exception, the exception handler is called, and then exception is type of exception is handled. What's the problem? Because add instruction is already completed the register file. The integer register file is already updated by this add instruction. And then we need to avoid actually this case. So actually, the out of completion is applied, then we cannot support the precise exception. Okay, and then this is actually critical problem. So we need, in order to support the precise exception, then we need to avoid this case. So which means that if the exception is detected at clock cycle 7 here, and then before the exception is detected, the following instructions avoid updates in register file or memory. Then you know this is very difficult. Right. How about the store instruction? If the store instruction is stored, so actually this is very critical. In a computer processor, updating architectural state is just a very critical issue. And then, so which means that, so that's why the data hazard or data dependencies also caused by this issue, like data updates in the register file or the memory. Also, some other issues like memory coherence or memory consistency is also very critical in the multi-core architecture, but it's also caused by data updates like store instruction. So also, it's very critical for the exceptions. So not to support the precise exception, we need to avoid this case. So how can we solve this case in the static pipeline architecture? How can we solve? It's not easy. So possible solution is one of the possible solutions is ignoring precise exceptions, but it's not a good option because as you can see, it's not a viable option. It's not a viable option today. So actually, we expect that processor supports precise exception, but if we processor ignore the precise exceptions, then you may think, oh, this processor is not good. So it's not a good option. So, okay. So sometimes, even though the precise exception is not supported, then we can also support the exception handling with the software. So which means that software can take some architectural space, and then software can estimate when and where the exception happens in the process architecture, and then software has just to report some exceptions to the operating system or visual applications. It's not a good option also. It's not a good option either, because it is possible only for the very simple pipeline architecture, very complex architecture. It's not a viable option in the complex pipeline architecture. So first option is to ignore precise exception, but it's not a good option. And then another possible solution is that not to support the precise exception, then we need to consider this case. Then if the exception can happen in the the last stage of the floating point 5 or the memory stage and some other stages. So then we can store this add instruction in the id stage. So which means that we can handle the exceptions like data hazard. But you know, it's not a good option also. But actually, if we consider the performance of the processor, it's not a good option. Okay. So we can handle the exceptions like data hazard. So which means that exceptions can happen in the FP5 stage, and then in order to avoid the register write and by this add instruction, the add instruction can be stored in the id stage. So which means that even though there is no data dependencies between this floating point add instruction and then the integer add instruction, and then but in order to support the precise exceptions, we can handle this add instruction like some data hazard. Okay, it's ridiculous actually. So if we just consider the performance, it's not a good option. The performance will be degraded very much, so it's not a good option also. So another possible solution is the implementing in order compilation. So which means that in this example, the processor architecture here on this side. So we can find that this is the integer path and this is the floating point path. And the integer path will take 5 cycles, the floating point path will take 9 cycles. So because of this default latencies between the integer and floating point instructions, and so this each is we cannot support the precise exception. So we can force in order completion like this. So which means that even though the integer type instructions does not require additional stages after this memory stage, it just make integer type instructions pass through the additional stages of the floating point instructions. So write back is performed in the after this stage of the also for the integer instructions. So which means that we can make the returns of the integer instructions like 9 cycles. But the write back is performed here. So we can support the precise exception like this. But what is the problem? What is the issue? Actually, we can make the more folding path. So we can solve the data handler by making more folding paths. Also, we make the folding path for the integer instruction from here to here and here to here, here to here, here also. So we need more folding paths for integer instructions in this case. So the control logic can be more complex, but in order to support some precise exceptions, then we can apply the in order completion like this. 네? 네. 그러니까는 여기서 인티저는 아무것도 안 하지만은 그냥 사이클을 소모를 하고 파이프라인 스테이지를 건너가게 하는 거죠. 그렇죠. 아웃 사이클. 그러면은 레이턴시는 늘어나긴 하지만 어쨌든 데이터는 이제 레디가 되잖아요. 여기는 뭐 메모리 인스트럭션은 여기서 레디가 되고 인티저는 여기서 레디가 되고 여기서도 어차피 다 레디가 된 상태니까는 포워딩을 시킬 수는 있죠. 뭐 데이터 디펜던시가 발견되면은 포워딩을 시킬 수도 있고 뭐 이렇게 되면은 사실 와우 해결도 해결은 되고요. 뭐 그렇긴 한데 좀 더 복잡해지긴 하죠. 네, so we can support another comparison like this, but not to support the precise exception. So I said that the exceptions are very rare cases, but processor need to support also these common cases. Okay. Then let's think about the super pipeline, the CPUs. Super pipeline means that actually why do we apply the pipeline architecture, the pipeline, the CPUs? So benefit of the pipeline, the process is that we can reduce the critical path that is delayed by some the required stages. So we can decrease the critical path, and then if we can reduce this critical path delays, then we can apply the higher clock frequencies. That is the benefit of pipeline CPU or pipeline processors. So then we can make additional stages for the instruction fetch or instruction decoding, and then some additional stages for the memory stage like this. So what is the benefit? We can also reduce the critical path for each stage. Okay, which means we can apply higher clock frequency. So higher clock frequency too. So the benefit of the super pipeline CPU is that we can apply higher clock frequency. So actually, we super pipeline CPU means that the stage, the number of pipeline stages is higher than the 5, so more than 5. So the benefit is the higher clock rate. And then what is the disadvantage of this super pipeline CPU? So this is the updated latency and then interval information of each type of instructions. So if we apply this super pipeline CPU, then we can apply the 2 stages for the integer execution. And this is the floating point, and also we apply the 2 stages for memory operations, which means that the required latency, if the data dependency is detective, the required latency for these instructions will be also increased. So which means that the performance overhead by data hazard also increases. As you can see, you can find that latency is also increased. And then another problem is that control hazard also increased. Control hazard increases. So the control hazard means that if the branch is taken and the following instruction in the pipeline stages will be flushed. So if we apply the super pipeline CPU, and then if the branch is reserved after this EX stage, because we need to compare the 2 different operands by the branch instruction, then which means that we need to flush instructions in the former stage, these more stages, which means that the control hazard also increases. So the problem is that the performance avoided by hazard increases for the super pipeline CPU, and then it's also true for the actually the history of processors. So you know actually so the AMD and Intel also apply. So actually the AMD tried to apply the higher clock frequency than Intel. So then how can we apply the higher clock frequency? If we increase the number of stages in the pipeline architecture, then we can apply higher clock frequency. So actually the AMD tried to increase the higher clock frequency. Then AMD advertised that our CPU can exceeded higher performance because we used higher clock frequency, but it was not true because the performance is degraded by data hazard or control hazard. If the number of stages of this statically pipeline processor increases, and as you can see, the performance avoided by data hazard or control hazard increases. Actually, that is the very critical issue. As another possible architecture is the superscalar processor. So superscalar means that the processor can fetch 2 instructions in every cycle. 2 instructions every cycle. So which means that in this example, you can find that 2 instructions are fetched for clock here. There are 2 instruction fetch engine. Then the instructions are decoded. But you know, in this example, the integer pass and then floating pass is separated. So which means that the superscalar CPU, we can fetch more than 1 instructions. And then what's the benefit? So if we can fetch the more than 1 instruction, then we can increase the performance. So how can we implement this superscalar CPU? Actually, the some required hardware resource is very small. Why? Because I already explained that in order to support floating point instruction, there are separated integer type register file here, and then the floating point type register file here. Okay. So there are 2 separated register files, like RF for I, then RF for floating point. So actually the required hardware resource is the instruction fetch engine for integer type instruction and then floating point instructions. Okay, so 2 instructions are fetched. So and then actually this fetched instruction is grouped like the integer type instruction and then floating point instruction like this. So compilers can generate the instruction pairs such as, and then every instruction pair has 1 integer instruction and then 1 floating point instruction. This is the superscalar CPU. So so additional hardware resources is just the 2 instruction fetch engine for the multiple instructions, and then the instruction decoder is actually we already supports the integer type instructions and then floating point type instructions. So instruction decoding is actually the same. So and then because there are 2 separated hardware engines for the integer and floating point instruction, so this is the good option. So and then what's the expected performance benefit? So So we can expect that the two instructions can be executed every cycle. So we can increase the performance by twice. So that is the expected performance. Okay. So in this case, we can use the IPC instead of CPI. The IPC means the instructions per cycle. So actually, if we use the superscalar CPU, then expected IPC is the peak IPC. So it's the ideal IPC is the 2, because this processor can execute 2 instructions every cycle. So it's not true. It's an ideal case. And then actually our world is not ideal. So actually when we compare the performance of the processor, we use the CPI because we can calculate the execution time with the CPI instruction count multiplied by CPI multiplied by clock period. This is the execution time equation. But for the superscalar CPUs and we can use the IPC instead of the CPI, which means that IPC is the inverse of the CPI. So if the IPC number is high, which means that the performance of this processor is also high. So IPC is proportional, the performance is proportional to the IPC. So expected IPC for this CPU is the 2. But problem is that enough to support, enough to achieve the IPC of 2, then the compiler needs to find every instruction pair like integer and then floating point instruction. So compiler needs to find this pair, integer and floating point instruction. But you know, this is very, very difficult. So number of integer instructions and the number of floating point instructions are not balanced in all normal applications. Okay, oops. So floating point instructions and the integer instructions are not balanced, so we cannot. So actually, the compilers cannot find available instruction for this every instruction pair. Okay, it's the problem of superscalar CPU. So, and then we can actually, as I explained, the control hazards are also very critical for the performance. So then we can apply the branch prediction. But so in the static pipeline, the process architecture, I will just briefly explain about the static branch prediction, because the branch prediction is critical for the, actually dynamic branch prediction is very critical for the out-of-order processor architecture, like Thomas Long algorithm. So the first, we can apply the static branch prediction. So which means that the processor just predict the result of the branch instruction for the only one direction. So which means that, so actually, if you, when we learned about the simple 5-stage pipeline architecture, so actually the static branch prediction is applied. So we assume that the result of the branch prediction is always not taken. Okay, why? If the branch is taken, branch is like a conditional branch instruction is taken, then the PC is changed by target of the branch. So which means that we need to perform jump in this case. So, but if the branch is not executed, so if there is no branch instruction, instructions are just executed from top to bottom sequentially. And then it's also true for when the branch is not taken. So in this case, if the branch is not taken, the processor just execute the instruction sequentially from top to bottom. So actually, the control hazards are caused when the branch instruction is taken. So which means that we already applied the static branch prediction, like the branch will be always not taken. So which means that we assume that branch is not taken. So the following instructions after branch instruction is just fetched and then decoded and then even can be executed in the pipeline processor. And then if the branch is taken, so which means that our prediction is wrong. So in this case, these fetched instructions are flushed in the pipeline stages. Okay, so it's basically the so we already used the static branch prediction, and then we just use the concept of always not taken. So actually, instead of this, we can apply the always taken option for the static branch prediction. So, but it's okay. But we can also apply the always taken option for the static branch prediction. But in this case, the target of the branch instruction should be also coded in the ID stage. So actually, there is some overhead by this always taken branch prediction. But actually, the compilers can analyze the branch instruction. So, for example, if we just execute the statement like for if I 0, I is less than n, I plus plus, and then some state. The statement instructions are here. So if we just see that this for iteration loop, then we can expect that a branch instruction can be generated by a compiler. So and then based on this n, we can estimate the number of iterations in this iterative loop. So compilers can also estimate the number of iterations in this case. So what does that mean? So in this case, the branch will be take maybe n times because maybe n or n minus 1 times. We need to calculate. But we can expect that this branch instruction is generated by this iterative loop in the iterative loop, and we can expect that this type of branch instruction will be taken many times. So compilers can also estimate the behavior of branch instructions. So actually, if we use the for loop or while loop or some other loop iteration, actually these loop iterations are widely used in our normal programs. The compilers can estimate the result of the branch instruction. So in this case, compilers can give hint bit. So it's a little bit different from the static branch prediction. So we cannot. So in this, the static branch prediction problem. So I mentioned that we can expect the result of the branches from like the always taken or always not taken. But for example, if we expect the result of the branch instruction as always not taken, and then if we just figure out this, so as you can see, this branch is always taken. This type of branch is taken many times, not always taken, but taken many times. But if the processor expect that, this branch is expected always not taken, then the performance overhead may be large. So in this case, the compilers can give hint bit like, for this type of branch, the branch will be taken many times. So the processor can apply the expect the result of the branch instruction like taken for this type of branch. If you use the iteration loop, and then compilers can give the not taken option for the some if as a statement. But it depends on the compiler's optimal estimation. So compilers can give a hint bit to the processor, and then based on this hint bit, the processor can apply the taken prediction or not taken prediction. Okay, but this taken or not taken, the branch prediction is also static because this the branch prediction is determined by compiler, not hardware. So these type of branch predictions are called static branch prediction. And then most of the modern processors use the dynamic branch prediction because actually dynamic branch prediction is it's very critical for the out-of-order processor architecture. Okay? Like Thomas Law algorithm. So actually the branch prediction is very critical. Then, but we can use this static branch prediction for the statically scheduled process architecture. Okay, the compilers can help the branch prediction with the hint bit. Okay. Compilers can apply some optimization technique by adjusting the order of instructions. Okay, because in the static pipeline architecture, and as I explained, the instructions have latency if the data dependencies are detected. Also, the instructions have some fixed. It's not true for the memory instructions, but usually for the arithmetic or some normal instructions have the fixed latency. And then, based on this information, the compilers can optimize the some instruction, the compiled instructions, which means the compilers can adjust the order of instructions based on some hardware information, like the latency or some interval of the instructions. We can distinguish the compiler optimization as the local optimization and then global optimization. So the local optimization means that compilers can adjust the instruction orders inside of basic block. So what is the basic block? It's very important actually. What is the basic block? DB. 아니죠. What is the basic block? So so basic block, actually the definition of the basic block is that if the first instruction of the basic block is executed by processor, then the instructions in this basic block is executed sequentially, that means in order until the end of the final instructions in this basic block. So which means that execution order inside of the basic block is in order. So it's sequentially executed. So actually the definition of the basic block is that the inside of the instructions in this basic block, the first instructions in basic block are not target of page block definition. The first, the instructions in page block are not target of branch or jump, except the first instruction. Except the first. And then the instructions in page block are branch or jump, except the last instruction. So this is the definition of page block. So which means that the instructions are executed on the inside of the page block, because there is no branch instruction and there is no target of the branch. So we can apply the compiler optimization inside of the branch page block. This is called the local optimization. So we can apply the global optimization across page block. Okay, so which means that we just group the page block as some large portion, and then compiler optimizations are just applied between page blocks. We can suppose loop learning is the representative global optimization technique by compilers like loop learning. So let's see this example, like the local optimization. Actually, it's very simple. The local optimization is actually very simple. So if we see this example, then this is the base block. Then, as you can see, this is the statement inside of the loop. So this is the base block. So which means that if the first instruction is executed, then instructions in this base block is executed sequentially, from top to bottom. So if we just calculate the required clocks for each instruction, then we can calculate the number of required number of cycles like this. So then we can find the data dependencies here, right? So F2, F2. So also we can find the data dependency from between load instruction to add instruction. So add instruction requires the 2 cycles because 1 cycle should be stored. And then we also find the data dependence between add and store instruction. So we can put it in 4 cycles. And then because of the control hazard, this is the iterative loop, and then that means that this branch is usually taken many times. So actually the 2 cycles are wasted more than 2 cycles are wasted. So the cycles for this branch instruction is 3. So if we just add the all required cycles in this base block, then this base block requires 15 cycles, so we can calculate the CPI. There are 8 instructions, so CPI is the 1.88. Okay, but we can optimize, we can adjust the order of instructions in this base block. So if we insert the independent instructions between 2 dependent instructions, then we can save cycles, right? So simply, in this example, we find that there is data dependency between load and add instructions. So we can find the data dependency here. So because of the low hazard, the cycles are wasted like this. But we can find some independent instructions in this base block here. So if we just move up this add instruction between this add instruction here, and then if we move down the store instruction to the end here, then we can reduce the wasted cycles. Okay, so as we instruct the independent instructions, we can load and add instruction. So this sub instruction just consumes the one cycle, but this is the required cycle. So we can register this cycle for the add instruction to 1. How about the store instruction? So store instruction is located just after the add instruction. So because of the data dependency, the store instruction need to wait 4 cycles. But by adjusting the location of the store instruction, and we can also just waste the cycle. For the branching, we cannot use a control hazard for this case. So what's the benefit? So execution time is reduced to 12 cycles. So the CPI becomes 1.25. So we can compare the performance. Like the performance improvement is the 1.88 divided by 1.25. Okay, you can calculate. So it's very easy. It's simple. So if we can find the independent instructions inside of basic block, then we can apply the compiler optimization technique very easily. And then, it compilers. So inside of the basic block, we can just adjust the order of the instruction. And then it's fine. It's very simple. There's no some critical issues in this compiler optimization. Okay, so it is very good. So what's the problem? The problem is that, oh, it's easy and then it's good and then it's free. But it's not easy to apply local optimization. It's because the size of the basic block is usually very, very small. And then it is known that the size of the normal basic block is about the 4.5. So it's between 4 and 5. What does that mean? The normal number of instructions in basic block is usually 4.5. It's about the 4 or 5. So we need to apply the local optimization among 4 instructions or 5 instructions. Then the problem is that it's not easy to find the independent instructions. So that's the problem. So local optimization is very easy, and then it's free, and then it's good, even good. But it's very, very difficult to find the appropriate basic block for local optimization. Okay? And the problem is that in this very small size basic block, it's not easy to find independent instruction. That's the problem. So what's the possible solution? First, the problem is that the size of a basic block is small. Then if we can increase the size of the basic block, then we can solve the problem. Now, how can we increase the size of a basic block? It's the loop unrolling. So this is the iteration loop, and then this loop will be iterated 100 times. Then so this loop will be repeated many times. So and then actually the one iteration loop has only five instructions, but if we unroll this loop twice, so that means that this we just unroll the loop and then just make this loop is execute this instruction, this statement twice for every loop, but loop is iterated 50 times. Okay, this is called the loop unrolling. So this is the loop unrolling technique. This is the original code, and then if the loop is unrolled, so the two iteration loop is merged. So we can just copy the instruction twice. But in these instructions, we can find that these instructions are used for calculate the offset of the loop. So, and then we don't need to also the last instruction, the branch instruction. The branch instruction is the just performs the jump in the loop. So actually, we don't need to use the branch instruction twice. We just copy the instruction, but we don't need to execute these instructions like offset calculation and then branch instruction. But just to remove the unnecessary instructions. And then, so it's just, so when this loop is unrolled, so I should be I equal I plus 2. Right, so offset is should be changed. So we just adjust some increment the offset of the instructions here. And then the DME, so the branch instruction is finally located at the end of the loop. And then we can apply the local optimization. So because the size of the size of this base block is increased by loop unrolling, which means that we can find more independent instructions here. So we can adjust the order of the instructions in this bigger base block. Okay, so this is the loop unrolling. So let's compare the performance by loop unrolling and then local optimization. So this is the required cycles for the basic pipeline, and then also the right number shows the cycles by super pipeline architecture. Then the loop unrolling is applied, and then local optimization is applied for this bigger basic block. Then the total time is the 14 clocks. Okay. So when the local optimization is applied for the unrolled loop, So in the original loop, then the clock cycle was 15. But when the loop unrolling is applied and then optimization is applied, then the number of clock cycles is 14 for the unrolled loop, which means that it's the 7 clocks per loop. So what is the performance improvement? It's the 14 divided by 7. It's the 2.14. So what is the benefit? By unrolling loop and then by applying optimization technique for bigger basic block, we can improve the performance more than twice, higher than twice. Okay. And then if the super pipeline architecture is applied, the performance benefit is even higher. Okay. So this is the benefit of a loop unrolling. And then, okay. So I'll stop here. And then in the next class, I will also explain about some loop unrolling, and then in the next class, I will also introduce some Thomas Law algorithms out of the processor architecture, the base algorithm of the out of the processor architecture. Okay, so I will stop here. Then thank you for your attention. Any questions? 네.
API 아론의 사도가
네.
하고 나면 코어의 영향이
있겠죠. 이거는 어드저스트 해줘야 되는데 그거를 이제 고려를 하지 않고 그냥 옮겨둔 거예요. 물론 이제 그 여기 애드가 위로 올라가고 밑에 스토어가 있으면은 이거는 사실 고려를 여기를 이제 마이너스 4를 해줘야죠. 사실은 옵셋을 조정을 해줘야 되죠. 맞습니다. 네, 뭐 다른 질문 없으면은 네, so thank you for your attention and then see you in the next class. Bye guys.